Good morning, sir. My name is Harpreet Chhabra, final year student of BIT Sindri, pursuing BTech in Metallurgical Engineering. Today, I will give my presentation of my latest research work done as a winter intern in NML Jamshedpur for 1 month, under the guidance of Biraj Sahu sir. My topic of today's presentation is annealing treatment of medium manganese aluminum added steel for automotive applications. This type of steels comes under AHSS. So let's see what is this. Firstly, I will give you a brief introduction of this type of steels and then the experimental work that is done by me in the NML and that are results obtained from that type of steels such as same micrograph, tensile test, factography, XRD analysis, and at last the conclusion is provided to you about the till the work I have done at the till the work I have done. After hearing the topic of my presentation, the question first arises in your mind is what is AHSS? So AHSS is generally known as Advanced High Strength Steel, or it is sometimes also known as Extra High Strength Steel because of its complex shape and multi-phase microstructures that are generally used for the formation of this type of steel, and this type of steels are generally performed by precisely controlled heating and cooling process, and this type of steels are generally novel as compared to the other conventional steels. Various varieties of steel AHSS are available, but AHSS solve two distinct automotive needs by using two different groups of steel by DP dual phase steel and trip grade of steel. TRIP is generally stands for transform induced plasticity. So now the next question arises why we have chosen AHSS for automotive applications. So firstly, because it reduces in the greenhouse gases emission, that is CO2, and since this steel is light in weight, so it also increases the efficiency of the vehicle, due to which increase in the efficiency reduces the greenhouse gases, and also small car is benefited greatly by crash benefited vehicles because they are used for making bumpers parts of the car components. This type of steel are also durable and remanufacturer friendly. So now comes to the evolution of advanced high strength steel. So a graph is presented in the screen, that is this graph is known as banana curve, and in the left side of the curve are those type of steel, that is AHSS first generation steel, and the graphs that are at the topmost right of the steel are known as AHSS second generation steel, and in the middle of the part, that is in the circular part, you have seen that future opportunities of third generation steel is the AHSS third generation steel, in which I have worked in this type of steel, as it comprises of properties of both the first generation and the second generation of steel with low alloy content. So now the experimental work of aluminum added medium manganese steel, that is generally known as third generation AHSS. The composition which is used by me during the procedure of the making is Mn contains 7 to 8%, aluminum 3 to 5%, silicon 0.3 to 0.5, carbon, that is medium carbon steel 0.25 to 0.35%, and nickel 3 to 3.5%. So lightweight steel generally consists of substitutional elements such as Al and Si that is present in it, and where the role of this element is to optimize the austenite stability by suppressing cementite formation. Furthermore, Al in the trip steel encourages the growth of intercritical ferrite and facilitates the presence of delta ferrite during solidification, contributing to excellent tensile properties. Ferrite is a soft phase with good ductility which helps to stabilize the austenite phase. For the purpose of obtaining lightweight steel that combine with high strength with high ductility, aluminum is added into the medium manganese containing trip steel. So now this type of steel, after the production of this steel, processing is done, that is hot rolling, cold rolling, intercritical annealing. Intercritical annealing plays a very important role for the property determination of this type of steel. So the parameters for intercritical annealing is temperature and time. So I have taken two temperatures, that is 790 degrees Celsius and 810 degrees Celsius, and I have taken time constant for both of the temperatures, that is 1.5 hours. The 790 degrees Celsius and 1.5 hours is taken as sample 1, and 810 degrees Celsius and for 1.5 hours is taken as sample 2. After the intercritical annealing, quenching is done, water quenching is done. Now It's time for the results and the analysis after the intercritical annealing. Firstly, we will deal with the microstructure analysis by SAME and elemental point analysis in the phases and the mechanical testing, that is generally tensile test, and then factography and the XRD analysis. After that, we will deal with conclusion. So here are the same micrographs for the sample, that is intercritical annealed at 790 and 800 degrees Celsius. So in the figure we can clearly see that the delta ferrite, that is the elongated structure, and the austenite, that is another structure that is just besides the austenite, and another structure that is the intercritical ferrite is formed. So we can clearly see that in this and 790 and 800 degrees Celsius that the delta ferrite shape changes, and from this we can determine that the tensile strength must be greater in the tensile strength, that is the elongation must be greater in 790 degrees Celsius. Let's see further whether it is right or wrong. So here is the elemental point analysis after the intercritical annealing in the phases by ADS. So we have three different phases that are found in our sample, is alpha ferrite, austenite, and delta ferrite. So the different composition are present here. We can clearly see from this and take a difference of the different samples. Now after this we have done the tensile test of the sample, and you have seen the tensile graph of the two different samples are seen, that is sample 1 that is in the black, that is for 800 degrees Celsius, and the sample 2 that is when intercritical annealing is 790 degrees Celsius. So we are right, the 790 degrees Celsius have greater elongation percentage than the 810 degrees Celsius. So from the tensile test, following data is obtained. For 790 degrees Celsius, yield strength is 678 and the UTS is 956, and the total elongation is 42%. That is very good elongation for the production of used in the automobile production. And for 810 degrees Celsius, so 608 is the yield strength, UTS is 814, that is very high UTS, and the total elongation due to which it reduces to 25%. So from this we can make a point that the intercritical annealing plays a very important role for determining the different properties for this type of steel. So after such a increase in the temperature, intercritical annealing temperature, there is such a decrease in the elongation. So I have taken the factograph of both the samples, and I got the results why it is have happened. So in the figure 1 we have clearly see that the delamination along the edges is done in the 25% elongation sample, whereas in the sample 2 we have got elongated dimples, which is the formation of which will generally tell about the ductile fracture of the material. After that, I have taken the XRD analysis of the sample which have got the higher elongation. So, and the data for this elongation are, we can clearly see that alpha ferrite weld percent is 50% and the gamma, that is austenite, is 49%. That this condition is before the deformation. Now this XRD is after the deformation, and we have seen that there is a very little decrease in the gamma. That means the alloying elements are playing their role in the formation of the in the formation of such type of steel. So now it's time for the conclusion that after the intercritical annealing, fine-grained austenite and ferrite are formed and elongated delta ferrite, whereas elemental partitioning takes place of the Mn and C took place to austenite, and Al and Si were partitioned to the ferrite. There is no significant partitioning of the Ni was observed, but the elongation percentage, that is the yield strength, increases, and the elongation increases to 42% because of the presence of the nickel, because it increases the staking fault energy, due to which no trip effect is done, and the generally the planar slip, that is gliding, is generally performed. So and this further work is done in the research, in this research for the production of such type of efficient materials. I would like to thank Mr. Biraj Kumar Sahu sir for giving me such a good project for doing the work, and I would like and thank the director of the National Metallurgical Laboratory for giving me the work or providing me the opportunity to do this work, and Dr. Sandeep Ghosh Chaudhary for providing me the facilities in the MT department for doing the project. Thank you, NML.